Very importantly, I would like to bring to the table here that corrosion management and integrity management move hand in hand. Asset life cycle management through integrity management approaches are extremely important in the payback to the shareholders. There's a lot of investment made into developing new assets and recovering important resources from the Earth's crust in terms of both subsurface facilities, which are wells, bottom hole equipment, Christmas trees, all the way to structural platforms. You've got the piping systems on the platforms, you've got the vessels, you've got static equipment, you've got rotating equipment, ranging from pumps, compressors, power generation equipment on platforms. All of these need to serve their design life with all risks kept as low as reasonably practical in order to make the entire investment or realize value out of that investment. So asset integrity life cycle, or the asset life cycle and integrity management across the entire life cycle, is a very important aspect. We manage it through two important philosophies. One is managing integrity through the project phase of an asset. The second is managing integrity through the operational phase of an asset. And as I mentioned, corrosion management is a subset of integrity management. Corrosion management in different stages of a development project. When an asset is to be built, we do an early stage conceptual study of an asset. We understand, okay, if you have a set of fluids that are expected to be recovered from the reservoirs or the formation, then how do we design the facilities in order to balance out the return of investment against the design life? So at the design stage, we decide on what the design life should be. We do a initial corrosion risk assessment study, as seen here as CRAS. We talk about material selection at a very early stage in design life to ensure that the economics are properly addressed. Corrosion threats are recognized very early in the design stage. Corrosion mitigation measures are thought about, philosophies are put in place. The QA/QC needs of development phase are well defined. Materials and corrosion deliverables are clearly defined at the design stage. This is a very important aspect. When things go wrong at the design stage, the recovery is very, very costly. I've been party to some very, very serious consequences of design problems. And I can tell you that that is one of the areas where universities like NTU and others who focus on corrosion can actually contribute, in fact, to the learning. So how do we do it? We translate our experiences to you as university, both as staff and students. We see how research can help us solve some of our collaboration issues. We bring in early new concepts on how to manage the design phase and the aspect of designing for corrosion control. Construction phase, there are a lot of things that need to be taken care of. Your design has to be translated into a practical, physical asset. You can imagine the challenges there. You've got to manufacture materials. You need to protect these materials. We need to ship these materials. We need to, from a shipped product at the site, you need to start constructing. So there are numerous environments through which these materials actually go through. So you need to delve and develop practices for protection and preservation of materials all through these stages before construction occurs. After construction, you need to preserve them until they actually are put into service. Then comes the corrosion control that you have in the design phase, becomes applicable. You need to ensure that all the controls are in place during the operational stage. Operational parameters are well monitored. Corrosion control is managed effectively. Corrosion monitoring is a very important thing. Just like monitoring your own health, you need to periodically check yourself for any changes that occur and try to manage it such that your health is sustained. Inspection planning, very important aspect. Chemical management, undoubtedly a very important aspect, especially where you have carbon steel materials used primarily in oil and gas business, in the water injection systems, in the conveyance or transport of fluids through subsea and above ground pipelines, underground pipelines. We use a lot of carbon steel, which goes with chemical management and chemicals used for corrosion inhibition and corrosion control. Regular coating and coating repairs are a very important aspect to deal with. Cathodic protection undoubtedly goes with most of our subsea and underground structures are all protected with cathodic protection effectively to ensure that the assets have meet the design level. I touched upon material selection, an important aspect, design for corrosion control, material corrosion deliverables. Just would like to touch upon this life cycle. As you see here, concept, design, build, commission. These are the development phase. The development phase is from concept to commissioning. The operating phase in this diagram is from the operate to the the change, improve, and abandon phase. So at the abandon phase of obviously you get rid of an asset safely. Assurance of integrity and corrosion occurs across all these parts of asset life cycle. Materials used widely in the oil and gas industry: ferrous alloys, corrosion resistant alloys, non-ferrous alloys, non-metallic materials. You've got a range of these shown up here. One thing I would like to mention here is that as we move from ferrous alloys to corrosion resistant alloys, they're on to non-ferrous alloys, and especially in the metallic range, you tend to increase cost, especially capital cost. So the capex goes up. Obviously, you have advantages around corrosion. However, depending on the design life and the economics of production, you may have to choose the ferrous alloys, which are not essentially corrosion resistant by themselves. They need to be protected additionally by coatings or by chemical treatment, by cathodic protection, proper alloy design, and so on. That's a very important aspect of materials. Another important field of application, another set of materials that are used heavily in oil and gas at the moment are non-metallic materials. GRE and HDPE, we are looking for contributions in terms of research inputs for developing the use of non-metallics, particularly in our region, the Middle East, because the economy runs around oil and gas. And these days, GREs and most of the non-metallic materials, the source is oil and gas. So they want to move to a complete end-to-end capability to manufacture non-metallic materials in-house in the Middle East. Damage mechanisms. I'm not going to go through everything, just to tell you here that API RP571 deals with most of the damage mechanisms that affect fixed equipment in the refining industries. We use this as a reference for upstream oil and gas design as well, to the extent that it can be. We understand some very important aspects and use it in our design for corrosion control philosophies. Damage mechanisms can be defined. I'm not going into the definition. All you need to, or I would like you all to sort of, I would like to share with you that damage mechanisms, understanding damage mechanisms is a very important aspect of integrity management, in that whenever you suffer a damage, we do a metallurgical or a materials failure analysis, investigation, and root cause analysis. Damage mechanism is an integral part of understanding how a material behaves and can see damage. In the upstream oil and gas business, we are focusing on mainly corrosion mechanisms that occur in the process side of equipment, primarily due to acid gases like CO2 and H2S. Flow-induced corrosion is a threat, of course, and environmental corrosion damage, which includes soil corrosion, seawater corrosion, atmospheric corrosion on the external side. Number of environmental assisted cracking mechanisms are also a source of failure in our facilities, which need focus and understanding, of course. Example of stress corrosion cracking, example of erosion damage and under deposit corrosion here. I'm not going to go through this, but I can tell you that there will be a time shortly when maybe we can collaborate to understand more about CO2 corrosion, H2S corrosion, a combination of acid gas corrosion, both CO2 and H2S together in internal oil and gas systems, internal corrosion in oil and gas systems. We probably can have opportunities to collaborate, learn, so that possibly through internships, people can pick up more about what internal corrosion is all about in oil and gas. Microbiological influence corrosion is a major threat, particularly for equipment exposed to seawater. You've got problems associated with biofouling in the first place, and then second is sulfate-reducing bacteria, especially in anaerobic conditions, which develop from oxygen scavenging that's done to seawater prior to either injection. And in oil and gas systems, wherever you have seawater contamination, you have the risk of sulfate-reducing bacteria as well. Stress corrosion cracking cannot be overemphasized at any point. It stands to be a major threat for most of the austenitic stainless steels and some of the higher alloys as well. Crevice corrosion damage can render a part useless, especially where you have a combination of different materials or coatings or deposition. You can have crevice corrosion occurring due to conditions either in the environment or the metallurgy or the materials aspects. Galvanic corrosion, we've looked at it from fasteners in outdoor environment, especially in combination with the galvanized parts. You can have corrosion where you have exposed carbon steel, for instance. Erosion corrosion damage. We did talk about damage mechanisms earlier: erosion corrosion, under deposit corrosion, external corrosion, external atmospheric corrosion. This is more or less a more detailed version of the description I had earlier that I had taken you through on the asset development phase. I'll not delve deep into it. We probably can have it discussed if there are any questions. Corrosion management in the operations phase, as I mentioned earlier, all these aspects: internal corrosion monitoring, fluid analysis, chemical injection surveillance, pipeline maintenance, pigging, very important aspect in managing subsea pipelines or most of the crude gas water transportation pipelines, especially. Monitoring of water quality, downhole corrosion inspection. Going on to chemical management, inhibition, biocide treatments, and scale inhibition. All of these have very important roles to play in oil and gas corrosion management during the operations phase. We have different ways of presenting data. What you see is a very primitive way of doing it. Today, we've fully integrated computerized systems in place which help us manage corrosion, help us know what's happening as a trend continuously in order to help us proactively manage corrosion. it would be incomplete to say that once we've designed, everything goes well. Now, we have numerous failures in our facilities. We learn from failures. We learn from investigation of failures and root cause analysis, as I mentioned earlier, tracking of actions, status reporting. All of these play a very important role in mitigating threat and risk, and thereby ensuring good return on investment for shareholders. Sharing of lessons learned. There will be hopefully future sessions where I can bring across to you some of the very, very important lessons we've learned in our industry. I'll be happy to do that in future sessions. Management of change, no doubt, we need to know how to manage change. You see, any changes in the design can bring about catastrophic results if we don't manage change well. So it cannot be overemphasized again. Corrosion control and chemical treatment all deserve proper understanding of change and managing the change precisely, I would say. Thank you, and that brings me to the end of this this presentation. I would now leave the floor open to question and answers. You've been very kind in keeping quiet, but I would like this session to be highly interactive. I'd be happy to receive any questions. I believe that learning is a continuous exercise. I learn today, I will learn tomorrow, I will learn until this life exists. So I think there's nothing like a stupid question. There's nothing like a stupid question. Please feel free to ask questions. We learn out of the questions that you ask, and I'm very sure you would also learn from the interaction here. Thank you very much. I would also leave the floor open to fellow professionals who joined us today to help us answer some of the questions where I might not have the exposure. Thank you.
So, Mr. Sampath, a question is, what are some of the practical methods that can be used to manage steel corrosion for structures and pipes?
Okay. I'll answer the question in two parts. First of all, for pipes, we see pipes are used in different applications across the oil and gas industry. We use pipes for a form of pipes called, well tubing. So in well tubing, they extend all the way from the surface of the earth down to about 10,000, maybe 10,000 feet below. Right, and these are long pieces of tubing that need to be protected and corrosion controlled. So there we use methods like squeezes of corrosion inhibitors into the reservoir and the formation, which then come along with the fluids and ensure that the environment as well as the steel interact in order to produce what you call as corrosion control. We use chemical treatments like film forming corrosion inhibitors. They are an organic product which film the surface of steel and produce the barrier that you need between the aqueous phase and the carbon steel surface, thereby improving corrosion performance. Other methods include material design. You could go for higher alloys. For instance, you could use special stainless steels. You could go to nickel alloys, but they're a very costly substitute for carbon steel and corrosion inhibition. That's on the pipes. On the surface, we use pipes for various applications. We use it topside piping. We use it in subsea pipelines. We use it in cross-country pipelines, both buried as well as above ground. So various methods of corrosion protection we use there. We use the simplest that I can think of for external corrosion is coatings, applicable for most atmospheric exposures. But in addition to coatings, especially for subsea and for buried structures, we use cathodic protection to supplement coating-related protection measures. On internal corrosion, especially in pipelines, transporting fluids, we use additionally what you call as biocides for certain applications where the threat of microbiological induced corrosion exists. We also use mechanical processes like, just like how we brush our teeth, you need to keep the teeth clean to avoid bacterial growth. So we use pipeline pigging operations. They are bidirectional brushes used to clean pipelines, and they are moved through the flow. So there are many such applications of mechanical devices used to control corrosion internally in pipelines. So that's about pipelines, I think, in brief. On the structures, especially offshore structures, they are sitting in the sea. They're exposed to aerated marine environments, both in the sea where they are exposed to water, and the sections outside the sea level or above the splash zone. You have structural steel exposed to the elements. You've got air laden with moisture, humid environments. You've got salt that deposits on surfaces. You can have very high rates of corrosion, all the way from about a few mils per year to about 1.5 millimeters per year, which means you can have the structures degraded within 10 years, probably. So it's important for us to protect them with coatings, high performance coatings. In fact, at splash zones, you use high thickness glass flake, what do you call this, GFB or vinyl ester coatings. In addition, we can use sheathing with non-ferrous alloys like Monel, which are used to protect the external surface of splash zone areas of structures. I hope that answers your questions.
Okay, thanks, Mr. Sampath. We'll move on to the next question. What materials do you normally use for cooling water heat exchangers, and how do you manage the risks in cooling the water systems?
Okay. One of the things I can probably relate immediately to is, I don't know how many of you are familiar with typically process cooling applications using heat exchangers. We have one side is the process. It could be either the shell side of a heat exchanger, or it could be the tube side of the heat exchanger. The other side is the cooling side of the heat exchanger, or with the section of the heat exchanger that carries the cooling fluid. In a cooling water cooled heat exchanger, you use cooling waters ranging from heavily desalinated waters, which could be almost, it's not potable, we call it utility waters, which are where salt is removed to a point where you have the total dissolved salts no more than about 250 ppm or milligrams per liter, very low in salt content. They're additionally sometimes treated with corrosion inhibitors and scale inhibitors and so on, just to ensure that heat transfer surfaces are protected. On the process side, it could range from crude oil, you could go into hot gases, go into gases that have high levels of H2S. You can imagine how important these heat exchangers are. Heat exchange tubes are typically no more than 3 millimeter thick, typically. And they can be down to less than a millimeter thick. So they are, and they need to last without loss of containment. So they're very critical pieces of equipment which can lead to cross-contamination. If you have the cooling water contaminated with the process fluid, you can have a whole set of problems in the cooling water side. Similarly, if you have the cooling water entering the process side, a different set of problems on the process side. Yeah.
All right. Okay. So the next question is, FPSO often face a major issue such as corrosion under insulation. What best way to prevent such issue during the designing phase?
Very interesting question. Actually, I'm not very sure whether Gautam joined us in this meeting.
Yes,
he's an expert.
Ghosh is, I think, around.
Yeah,
Dr. Ghosh is a mentor of Mr. Sampath, and he is, just let me pull up the information. He is from Modec Offshore Production Systems here in Singapore, and he is also a materials and corrosion lead. So if Dr. Ghosh is around,
maybe he has a problem in connecting in because he is working at the moment. You know, he works to Singapore timing.
I see. All right.
It's quite possible. You see, you know, it's 1st of October, a holiday for me. Friday is a holiday for me here in the UAE. So I'll answer the question. Well, corrosion under insulation is a problem, particularly where you're dealing with components of a process system which goes through changes in temperature. You got temperature changes from less than normal room temperature, very low temperatures, possibly in winter, all the way to, let's say, 100, 120, 150 degrees C. And if it oscillates between these temperatures, what you have is a surface that could well become wet and dry, wet and dry, wet and dry. You know, several iterations of this happening and repeats. When this happens, you have a gradual, especially in marine environments. So when you're talking about FPSOs, you're actually talking about production vessels that are always in the sea. They're exposed to atmospheres laden with salt and water. So the moment you have these fluctuations, you will have a constant buildup of salt. And when you have a buildup of salt and you have again wetting, then you've got a very high concentration of salty water on the steel surface. How do we address these issues? We address it through the design phase, incorporating the right combination of surface coatings, surface preparation, coatings. Coatings are designed for immersion surface. That's the level of quality of coating that is required in general to manage corrosion under insulation. Coatings that can sustain the temperature changes without cracking or loss of integrity of the coating resulting permeation. That's a very important aspect. And then looking at insulation materials that can keep away water. That's a very important thing. You can either have a material that will reject water, or a material and a combination of external protection that will prevent water from getting into the system. So a system that does not breathe, in fact. So design is a very, very important aspect in preventing corrosion under insulation, because most structures and equipment protected with insulation, it's very difficult to inspect them. So all you need to do is to make sure that things are done right the first time in design and in construction. If that answers your question.
Okay, thank you for that answer. All right, I think do we have a new question? Maybe let's take yes. So the person who asked, one of our students, Yu Ting, said thank you that you were able to answer his question. Okay, so last call, one last question. We would like to wrap up. But before that, just a reminder to please help us answer the feedback form that I sent in the chat. And Mr. Sampath, are you willing to share your email address if they have any questions?
Absolutely, I have no problem. In fact, I was going to ask whether I think you mentioned that this this presentation has been recorded in full, including the discussions we are having.
Yes, yes, Mr. Sampath. Yeah.
I would appreciate it be shared with everybody as well as with me, and in the process you can pass my contacts to all attendees and others, whomever you wish. The idea is making the floor open and making it easy for anybody to get in touch with people like myself, Dr. Ghosh, who was connected, and I would like to tell that it's two mentors that I said I would bring on the stage today is Mr. Bharat, also who's helped me in my life in the past. They are the people who in the industry would be very, very happy to help students, in any way that they can.
Yes, thank you so much for that offer, Mr. Sampath. So in that case, I already put in your email address in the chat. So for the emails of Dr. Ghosh and Mr. I think Goeja, I think maybe I'll leave that out because we don't have their permission to put that in. But if someone emails you and you'd like to connect it with them, then please go ahead.
Certainly. Certainly.
So nothing is coming in here in the chat for now. So okay, the feedback form is not working. Okay, I'll put that. I'll amend it and send it to you. Okay. So Mr. Sampath, any last message or parting words for our attendees?
I have, in fact, something very important to make a mention here. I would like to talk about ADNOC's values. Which, as a materials and corrosion engineer, I relate a lot. Basically, the values say that first of all comes 100% HSE. There's nothing more important than 100% HSE. Health, safety, and the environment, we call it sustainability today. It's very, very important that we manage our health so that we deliver personal integrity. We bring on to the stage personal integrity first through being honest in our work, which is extremely important to the industry. I cannot overemphasize this. Apart from this, I would like to bring in the 5 different values of ADNOC to the stage as well. They are about being responsible, being respectful, being collaborative, being progressive, and last but not least, are you able to hear me?
Yes, we're able to hear you, sir.
Yeah. Last but not least is collaborative, progressive, and being efficient. In today's world, we need to learn to be efficient in our use of materials. We understand that materials are fundamental to any progress in any sphere of human development today. Materials are fundamental. What is important is to understand how we can efficiently use materials, reduce waste, find the best ways of engineering materials such that they last as long as they can, reduce the use of materials that are not biodegradable, materials that can cause irreparable damage to the environment. We have a very big role and responsibility to play here. And as corrosion engineer, I would like you to delve upon these 5 + 1 6 values. I think we can champion this as materials and corrosion engineers. That's my message. Thank you.
Thank you, Mr. Sampath. Okay, thank you for those who have clicked on the feedback form. Again, sir, thank you for sharing your experiences in the industry with our students, with our alumni, and the few faculty who are also in here. So for everyone, thank you for attending. We hope that you could share about this event to your friends so that when we organize another one, more people would come and also learn not only from Mr. Sampath, but also other speakers as well, who may be from other industries. Like you should really seize the opportunity for such a dialogue with our industry experts. Okay, thank you everyone. It's 4:13. Have a happy weekend and good luck on your CAs if you will have it next week. Okay, bye-bye everyone.
Indeed a pleasure to be here. Thank you very much. Bye-bye.